Okay, welcome. So one of the things I wanted to do now that we've generated our structural analysis Grasshopper definition with the Python code embedded is I wanted to show how we can use another component within Grasshopper to actually help us do something useful. So in this case, I want to optimize the position of two supports. So this is a simply supported beam, and I'm saying that we have a load P at this end and the same at this end, and then a load of 2P in the middle. And ultimately what I'd like to do is I'd like to optimize the value of A as a fraction of the total length in order to find the configuration or the position of the supports that will minimize the absolute value of my bending moment. So I've just set out the example here. We have the loading. I've drawn all of my positive conventions if we're using the cross-section axis system, but obviously remembering that the script or the definition will mostly work in the global axes, but clearly in the definition we have done the conversion to the cross-section axes. So it would be possible to find A using a fairly easy algebraic or graphical approach, but the component that I'm going to use in Grasshopper is quite an interesting component called Galapagos. And it basically allows us either to use an evolutionary algorithm or a simulated annealing algorithm. So to follow a optimization process that will allow us to find A in this case, but clearly we could use it for much more sophisticated optimizations if we decided to. So if we just look quickly at the shear force diagram, so remembering that we're interested in the internal force. So what that means is we know initially we have a positive shear force of plus P. As we go across the reaction at the support, so keeping in mind this is all symmetric loading, we'll go to negative P. Then as we go across the next applied load, we'll go to positive P here, and then finally negative P. And I've just indicated that this is the shape of the bending moment diagram. So when we're in this region, we'll have tension on the top of the beam. When we're in this region, we'll have tension on the bottom of the beam, and then similarly again. So our aim effectively is to find the position A to have our support. That means that the value, so the absolute value of the bending moment here and here and here will all be the same. So that's what we'll proceed to do with the Grasshopper definition that we've already developed in the previous video tutorials. Okay, so I'm picking up directly where we left off. So this is the previous beam example, the cantilever beam. So the first thing I'm going to do is alter the setup in terms of the input, and then I'll demonstrate how we can use this Galapagos component. So I'm just going to move the bifocals over, and we're interested, as I say, first of all, in going back to the beginning, so where we're actually generating everything. So what we want to do is we want to split our original line at particular locations, and they're going to be the locations of the support, but also the location of that central loading. So that's what we'll do in just a second. Okay, so we can use a shatter component, just like so. So we've used this before just to generate the number of elements that we wanted along the length of the beam. but this time we're going to use it to divide it up so that we know we'll have a node at each of the supports and also a node at the central loading location. So my central loading location, actually I just want a panel for that, and I'm going to say obviously it's at a distance or a parameter t just equal to 0.5. So we'll feed that in a second. I then am going to use a slider, and actually I'm going to have quite a large number of decimal places on this slider because I want Galapagos, when we use it in a few minutes, to find the specific location. And I'm going to allow it to vary all the way between being at the very end or at the start of the beam, and I want to allow it to go all the way up really very near to the midspan. We don't want it to go right to the midspan because that would cause a problem in terms of very small lengths of beam. So actually what I'll do is I'll probably just take it to 0.4900, but close enough, and then just hit enter. So the final one we want is obviously we want that slider or the support, but through the slider to control the position of a support at the other end. So I'm just going to say minus here, and it will be 1 minus that value. So just making very clear that 1 is the value we're putting in here. So just 1 there. And like so. And because I want to have all of these as splits along the beam, I'm just going to merge these all into one. So we'll have the first support, that load location at midspan, and then the second support like so. And although everything is fine there, I may as well just flatten this actually as well. I'm just going to change this slightly, the range in here. So obviously what I want to make sure is that we don't have a situation where we have a 0 length at the beginning as well. So I'm just going to change that to 0.0100. And because this is the parameter a in our setup, I'll just call that a like so. So we can then run our line into this, and then I'm going to run this into there. So this should give us, a total of 4 line-like curves. And I'm then just going to break this link here, basically. So I'm going to run that in there. Just in order that I can see the numbers clearly, I'm going to increase this to around about, well, a third distance, so that when I now come over here and I look at my list of node numbers, you can see what we have is we have 0 to 8 basically. Then obviously we go from 8 up to, I'll just reduce the size here a little bit. So up to 16 is essentially our midspan. Then we go along to 24, so that's the location of the other support. And then finally we go along to 32 there. So that's the end of the beam. And obviously the reason that we're interested in those, so I'll just show the lines for the elements, and we can see the element list there as well if we want. The reason that we're interested in those is obviously I need to edit my input. So I want a load at the start, so at node 0. I want double that load at the mid point of the beam, so that was node 16. So minus 20, I'm going to say, down there, and then finally I wanted a load at the end of the beam, so -10 I'll put there, and then 0. And then in terms of our boundary conditions, so now I want the first support at A, and I want that to actually be in the X and the Y, but not about the Z axis. And then I want my second support along at the equivalent place at the other end, so that was node 24. We don't have any axial loading, so it doesn't really matter what I do with the X component here, but I'm going to treat it properly as simply supported. So I'll just have a support in the Y direction, and again I don't want a support around the Z axis. So like so. Okay, so what we can now look at, I hope, is if I come along and I just look at my bending moment diagram, so we can see actually the form of it is such at the moment the bending moment is positive the entire way along, and hopefully I'll be able to get back to my slider. So as I alter the position of that slider, you can see that affects the magnitude. So obviously even without the Galapagos component, I could kind of play around with the slider here, and I could find the position where visually this value and this value, the absolute values, were around the same. But in order to demonstrate this evolutionary algorithm we're going to use with Galapagos, we'll go on to set it up. Okay, so we'll introduce the Galapagos component here. And it's a slightly strange component, so the only way you can connect to the component is by actually going from the component and then pulling back to the component that you're interested in. So the genome evolutionary algorithm, I guess, should probably give away. This is going to be any set of sliders, basically, so a variable parameter you can feed in here. So I'm going to pull that over to our A, and you can see very faint, there's a red line coming up here. And this is because we haven't yet defined the fitness criteria. So that's what we'll do now. So the fitness criteria, what we're interested in is we're trying to minimize the bending moment. And so the bending moment, if you remember, was the third and the sixth output from here. Because we're only interested in the magnitude, I'm actually going to take it from back here where we partitioned the list, so this series of 6 values each time. And I'm going to use a list item select. So let's get my list item there. So we'll feed that in here. This time I know that the index of the items I want, so I'm going to put this information in a panel. So it's 0, 1, 2, refers to the indexes of the first node, so it's index 2 from there, and then 3, 4, 5, so it's index 5 effectively gives me the value at the second node. So just changing that to multi-line data, and we'll just shrink that down a bit so we're feeding that into our item. As usual, we'll just turn the wrap off. So now you can see that I'm just getting 2 outputs each time, so these are effectively our bending moment values. What I want to do is obviously take the absolute of them, so I'm not interested in whether it's positive or negative, I just want the absolute value. What I can do from here, I'm just going to flatten all of that information, and then I'm going to use a bounds component. So that will give me from 0 just to the maximum value, the absolute maximum value. And then finally, what I want to do is I want to deconstruct that domain that I've just created the bounds for. So on here, the start will always be 0, and then the end is just whatever the maximum, absolute maximum bending moment we have is. And I'm just going to put that into a number component. So what all of this is doing, we'll just group it, and I'll say finding apps max of my, which is our internal moment. And obviously now what I can do is I want to take this number, and this is what I'm going to take back and use as my fitness. So I'm just going to add a number component here. So this will be my apps max bending moment. So just go find it over here. So you can see effectively this is creating a loop. It's quite an unusual thing to do in Grasshopper. It's not really the way we would normally work, but it's what we do for this very particular component. Obviously, to tidy things up, I could just hide that wire, but I'll leave it in place because we're emphasizing what this Galapagos component can do. And then, as I mentioned, we have to go from the component to the relevant component that we're using to assess the fitness. So in that case, we're doing this. So you can see we now have basically all of the information that we want. So I'm just going to group this little lot, and I'm going to say optimize parameter A, and that is giving us the support position. Okay, I'm going to take this, so parameter A, kind of just away from what might be the optimum. So we'll just show that. So this is very far from the optimum. Obviously, all of the bending moment is positive in this scenario. And then we'll zoom back in on here. You can read the blurb that pops up for the Galapagos component. But essentially, to open this, we just double click and we get faced with this. And obviously, you could have a look at the various bits of information in here. The main choice we have is whether we want to maximize or minimize our fitness output, basically. So in this case, we want to minimize the apps max bending moment. So I'll move that to minimize. We then have a choice of solver. So as I mentioned, we're going to use the evolutionary solver, but you might want to experiment with the simulated annealing solver. Once we start the solver, it will take a few minutes. So I'll just pause while it's running, but we'll start this off and you can see everything's moving along here. So essentially it's running through different populations and you can see the values here. So this is the fitness value. So the apps max, the minimum of the apps max bending moment, you can see it's gradually reducing. Okay, so this is now reached convergence, and we can just have a quick look down here. So at the moment it's showing all of our genomes. we can just show the top 50% or the top 25. So these are the ones that have the minimum or the lowest value of the apps max bending moment. Or what we'll do, we'll just show the top 10%. And you can see essentially these are getting lower and lower. If I click on this one, we could say reinstate, and what that'll basically do is it will take the value that it found as optimal for A, and it will input that into the Grasshopper definition. Or what we can do is just say OK, and what that should then do is it establishes, so it brings across the optimum value that it found for the parameter. In this case, that 0.1667, I'm sure you quite quickly recognize that as essentially 1/6, and you could go back to the setup that we had just to find out whether that seems reasonable or not. If we zoom in here, so we can show the bending moment diagram, that does look to be roughly equal there and there. Obviously I can zoom in so I can look at the values. So just because of the particular loading that I had, it turns out, and obviously the dimensions of the beam and so on, it turns out that actually the bending moment is, well, it's a multiple of that decimal. You can see we're very, very close to the exact values being equal. The other thing we can do, so obviously we can just check our gradient, so we can draw a gradient of the bending moment instead, and we can obviously zoom in and have a kind of look around on that basis, just like so. And then finally, what I'll do is I'll just show the the normal stress. So if we zoom out a little bit, we can see we've got those regions over the supports where the maximum tension values are in the top, and then obviously under that central loading, the maximum tension value occurs in the middle. So I'll just try and leave this on, and maybe actually we'll also show the bending moment diagram. And then the last thing that I'll do is I will change this to a deformed plot. So maybe I'll just turn off the numbers for a second. So just Control to turn them off. So we can now see that the displaced shape is fairly much following the bending moment diagram. And if I add in the final thing, what I want to do is just show the original elements so you can see how everything is happening in terms of how the regions of tension and compression are obviously reflected in the display shape, and also the bending moment diagrams. So yeah, hopefully quite a nice example of now how we've got all of this set up. We can do this optimization, and although we've obviously chosen an example where we could do this algebraically, clearly you can apply this to much more complex scenarios. So just as a summary, the component that we were interested in using is this Galapagos component here. So quite an interesting bonus of having all of this embedded within Grasshopper. Okay, see you next time.